like 15 minutes, maybe, just presenting a few topics and maybe questions which are close to my heart, I would say, and which are supposed to be some of the main subjects of our discussion. But of course, I cannot cover all the questions, directions, etc. So please try to be active in 15 minutes, and all the hopes are on you to have an animated discussion. Okay. So I will start from just pronouncing the standard phrase that n equals 4 super Young-Mills and ABGM model and maybe AdS3 CF2 duality are integrable in planar limit. And this raises a few questions, only partially answered, and a few comments. First of all, what does it mean to be for these theories to be integrable? It's not a usual integrability, not like in two-dimensional theories. We have some answers from this question, although not full understanding. Then what are the origins of this integrability? Still no complete answer. Then what is achieved due to integrability? Certainly not everything that we can achieve. And what else might be achieved? Okay, so the origins of this integrability are still mysterious, and we have only a few very pertinent observations, but only observations. So we have explicit integrability in the lowest orders of perturbation theory. Then we have quasi-classical integrability on the Walsh-Sheet sigma model. These are our main assertions which give us the conviction that the whole model is integrable. Then, of course, we observed some mysterious constellations in planar perturbation techniques, such as the domination of highest transcendentality in the graphs of physical quantities, whereas for usual Young-Mills, this is only a part of all possible graphs, although maybe the most complicated part. And also some of ideas of why the theory is integrable is given by the so-called fishnet CFT, a certain limit of gamma twisted n equals 4 super Young-Mills, where the integrability becomes explicit, and this maybe gives us chances for understanding the integrability of the whole theory. Maybe for me, it seems to be a thread pulling on which we could probably undo the whole ball of this mystery. Okay. Then, of course, we have many advantages, more complicated physical quantities like sawing amplitudes and multi-point correlators from pentagons, hexagons, octagons. There were a couple of talks on this conference on it. I will not speak a lot about it. So another important hint is localization and relation to matrix models, which is only partially hinting on integrability because it works usually even at finite n. Okay, and now I wanted to spend like 7 minutes on presenting at least my vision, which corresponds, to most of the details also coincides with the vision of a few people here in the audience, but maybe some details will be curious. I would like to present one of the main achievements of this field, the solution of spectral problem, and namely its most modern and maybe most promising form, quantum spectral curve. And I will first give, I think the scheme is now so nice and concise that I can really explain it on two transparencies. So it is based on a certain set of Baxter functions of spectral parameter. And all these spectral functions should be put on so-called Hasse diagram, should be labeled by Hasse diagram. Here, as a cartoon of our symmetry group SU 2,2/4 superconformal symmetry group, I give the analog SU GL4 Hasse diagram, which can be also SU 1,1/2. It's the same one. So all the Q functions are put on here on the vertices of four-dimensional hypercube, such that at the North Pole, say at the North Pole, we have Q empty set. Then its nearest neighbors are single index functions Q1, Q2, Q3, Q4. Then on the next level, like the equator here, there are double index functions which are the neighbors, say Q3, 4 is the neighbor of Q3 and Q4, etc., up to the full set, the South Pole, Q1, 2, 3, 4 in the curves. This is the labeling, and also there is an algebraic function which says that the whole structure of this QQ system is Grassmannian, namely on each face we have relations between these Q functions. For example, on this dashed face, the product of Q1 and Q1 to 4 is the Wronskian 2x2 determinant of Q1 4 Q1 2, like with all these characteristic shifts U plus minus I over 2, and that diminishes enormously, of course, the number of independent functions. You can think that there are 4 functions left, like, or 8 for the superconformal group of n equals 4 Young-Mills. And then we put some restrictions on these functions. Usually in bosonic case, we put restrictions on the Q empty set and Q full set, the North and South Pole, like 1 is 1, for example, and another is some power of spectral parameter, like length, for example. But for supersymmetry, we sort of turn this picture 90 degrees, and we fix rather the functions Q1, 2, and Q3, 4. The diametrically opposite functions, but the way you fix it depends on the model, of course. I will precise it for this particular case of interest. Okay, and then we have to give some analyticity conditions and gluing conditions, like monodromy conditions, which are well known for now for AdS5 CFT4 and for AdS4 CFT3 during the due to the works of the last years, but it's still to guess for AdS3 CFT2, where the things are complicated, but I think it would be a good beginning to think about it, these Hasse diagrams. And not everything is well known for AdS4 CFT3. For example, the Hasse diagram should be more complicated because this is OSP type of the group with this Dynkin diagram, which reminds rather D5 algebra, I guess. And for D5, as we know from one of the talks, we know how to construct Hasse diagram. Maybe it will be helpful here, but I'm sure this is the last touch to put on this nice spectral quantum curve for ABGM model. And finally, if we go to the actual AdS5 CFT4, sorry, here, then we take the 8-dimensional hypercube, we fix the these conditions on 2 functions, diametrically opposite functions, And we choose their neighbors as specific functions with specific analyticity. There are 8 functions, like 4 of them we call P, 4 of them Q, and there are functions Hodge dual with the opposite pole with upper indices. And we know their large U asymptotics, including even the twist factor for gamma deformation. And we know that they have P functions have shortcuts from -2G to G, where G is the only place where the coupling, Hopf coupling appears in the construction. Then we know the same about Q functions, but the asymptotics is given by conformal charges, and the cut is long, goes through infinity. And finally, we have gluing conditions. For example, Q1 is related to Q bar 2, where bar is the complex conjugate between 2 branch points. And that's it. And after solving these conditions, we extract and fixing all the charges except delta, we find usually the discrete spectrum for anomalous dimensions for any local operators, and with little modifications we can also do the same in Caspills and loops, etc. So this is the whole construction, and I think it still has to be at the heart of many other developments. And just a couple of words. I see my time is almost finishing. A couple of words about fishnet limit. As I said, it can give a hint about what is integrability. It's explicitly integrable in all loops, which we see, for example, from this single coupling version of this model, this limit, which is just the interaction of 2 scalar bosons with chiral interaction, non-unitary, unfortunately. And the Feynman graphs, the bulk of Feynman graphs is this fishnet, which you see here. But in the most general case with 3 couplings, one gets a more complicated sort of dynamical fishnet, still with a regular planar structure. Now you have 3 bosons, 3 fermions of 3 different colors, and you have 3 systems of lines, black at different angles, black, red, and green. Dotted lines correspond to fermionic lines, so you can decorate this picture with fermionic and bosonic lines in all ways, but the lines should be uninterrupted, of course. And each of these graphs, and then you can move like in Young-Baxter equations, you can move the lines without changing angles through all these crossings, etc. And each one gives new diagram. But the diagram is then from this picture, the particular diagram is restored in an unambiguous way by certain rules. You put Yukawa and 5-4 interactions here. So you still have a rigid, less rigid, but still rigid dynamical fishnet structure. And the question is, which I always, I think it's, the answer should be at some point affirmative, that maybe the whole n=4 is sort of a fishnet in disguise, that there is a hidden regular dynamical lattice structure for all planar graphs in the full n=4 super-Riemann. That's an interesting way of understanding the integrability. And of course, we have here explicit AdS CFT picture in terms of fish chain, a chain of particles on AdS. Then an interesting integrable 015 sigma model for dense fishnet graphs, etc. So this, what is difficult in the full model, we can realize here explicitly. And also integrable fishnet CFT exists in any dimension, and only in 4 and 3 dimensions we know the supersymmetric mother theory, the corresponding full supersymmetric theory. The question is whether in other dimensions we have such we can lift it up, lift the fishnet theory up to the full conformal theory. Okay, then correlators, amplitudes, I really don't want to spend time here because I repeat the pictures which everybody knows, and Benjamin Talks gave very nice, gave very nice presentation of these methods based on bootstrap with pentagons, hexagons, etc. I only want to, and he even hinted how we can solve the problem of singularities, which prevent of solving the problem in all detail, but but there are some other methods from integrability. Again, for the correlation functions, there are quite nice formulas for particular quantities, where the structure constants are given in terms of integrals of Q functions. There are various results hinting on it that Q functions can be central to this, as a solution of quantum spectral curve, can be central for restoring other quantities. We heard it also in the talk of Andrea. And finally, so there should exist some universal formulas of this kind. And finally, I just added this phrase because I was impressed by this new bootstrap approach given at the end of Andrea's talk, which hints maybe that the quantum spectral curve contains all the information about even more complicated quantities, correlators, etc. This last suggestion I found fascinating, and I invite to discuss it also. I invite you to discuss it also. That's it. Here I just show the basic questions. What is the origin of integrability? Did we solve planar super-Young-Mills? Is super-Young-Mills a fishnet CFT in disguise? And beyond the planar limit, do we what about the integrability of corrections? Coulomb phase integrability, there are questions about it, whether it exists. And also, what did we learn about integrability in high energy QCD? Maybe we have some relation to physics. Okay, here I stop. Thank you. And I show there are two sets of questions which were also on Slack, and I will show sometimes the first page, sometimes the second. So here I finish my little presentation and give the word to Lucia to lead the discussion. Thank you.
Let's thank Volodya. Okay, who wants to start? Yeah.
So I actually don't have any answers, but maybe I have another question that came to my mind, because there is a lively discussion, I think, in the string and AdS CFT community about the idea that maybe there is a way of thinking of holography that involves ensemble averages rather than a one-to-one map between theories. And this is something that has been seen on some examples, but in a slightly different context than usual. Well, AdS CFT is more related to maybe low dimensional example or other spatial theories. I was wondering if maybe Volodya or anybody else thinks that by integrability, since we have all this machinery that works for quite a number of theories, we have any chance to help give some insight on this question.
So the question is about lower dimensional integrable theories, the possibility of them. Is it the question about this AdS3 case, Alessandro?
I think it's more about these ensemble averages that appeared also in theories that are not related necessarily to integrability, but for instance, to Jacques-Teitelbaum and so on, right? Where it was seen that to get a holographic correspondence, you have to average in some sense over some set of theories. And I was wondering whether, like it seems that there is a bit of confusion on this point. There seems to be slightly different prescriptions. And I was wondering whether in the integrable framework or in the integrable zoo, we can study something that can give some insight on that.
Very interesting question, but certainly I don't have any insight. I remember what you mean now in JT gravity, namely sort of an effective matrix model, whatever it could be for AdS CFT, AdS 560 CFT4, but we are far from constructing something like that. Or do we really need it? What would it clarify here? Isn't AdS CFT duality enough? But certainly it's interesting. It's a question. I don't have any opinion, stronger opinion on it.
Okay, there's a question by Fedor.
Just maybe a small comment in the question to Alessandro. Are there other examples of this ensemble averaging except the JT?
Could you please stand up?
Sorry. Okay, so just a comment in the question to Alessandro. Are there other examples of such this ensemble averaging in addition to JT? So in JT, they find that this gravity is equivalent to a matrix model, and they say the matrix is actually a Hamiltonian. So we have an average over Hamiltonians.
Also in AdS3 CFT2, but not the integrable AdS3 CFT2. There are some examples where
okay. Alessandro says that there are in AdS3 CFT2 also some similar examples, not in integrable one, but in some others.
That's very interesting.
Okay, there's a question by Carlo online.
Okay, thanks. Vladimir. So is a question technical about the quantum spectral curve. Since we believe you understand the spectrum, I have two technical questions. The first is if you can, if people are trying still to get analytic results, a strong coupling from the quantum spectral curve, like imagine a few orders in 1 over lambda or 1 square root lambda of the Konishi dimension, for example. This is the first question. And the second question, since the quantum spectral curve is a well-defined mathematical remainder type of problem, if there is a chance to show completeness, since we know how to count operator in many, many ways, how to count single trace operators, can we show that the quantum spectral curve, the set of solutions to the quantum spectral curve with given asymptotic reproduces all the states, completeness issues? These two.
First of all, maybe I start from the second question. I think for a long time I have in mind that, because this is already, I think, even mathematically relatively well posed nonlinear Riemann-Hilbert problem, and we can already address to mathematicians or to mathematically minded people like you, maybe we can study it by the methods which are known in this Riemann-Hilbert theory, and to study this question. Certainly, I'm sure it's such a nice object that sooner or later it should attract the attention of mathematicians. And the question is whether maybe they will find some generalizations. Say, if you start from lower dimensional Hasse diagrams and try to impose various restrictions on Q functions. Kolle told me he tried it with this SL4 case, which I discussed, but if you copy what you do for AdS5, it's too restrictive, but maybe you lift restrictions and invent some new models on this side, and then try to guess what kind of conformal or superconformal theories are behind it. Or maybe we will encounter some anomalies which prevent us from building it. See, I think there should be a bigger zoo of integrable higher dimensional models. Maybe they are not local. Maybe they're not described by local Lagrangians, like Kostya once gave a list of the local superconformal theories without anomaly, sigma models, but there may be non-local realizations, like we see in higher dimensional fishnet, for example. So maybe in this way, and for conformal theory, it's not a big deal when it's non-local. Most important are the OPE, etc. So maybe it's a way to searching for new theories. That's what was my dream also. And your first question was about strong coupling expansion. I think at some point the problem was frozen. Also, some people from the audience promised to think about it, to build a regular one or lambda expansion. I think it's a beautiful problem, certainly more complicated than perturbation theory on the other side of duality, but this is, I think, a beautiful mathematical problem as well. No idea about any advances here. I mean, regular expansion, not just finding a couple of terms.
Okay, there's a question by Didina.
Yes, so I can jump from here to my question. So one of the most sophisticated, among the most sophisticated exact answers we are able to get, for the example, for the correlation functions at arbitrary coupling, they are expressed in terms of Fredholm determinants often. So these Fredholm determinants contain the answer at any coupling, and they hint at the existence of some fermionic structure. So first question is, can you see this fermionic structure at the level of the Q system? So the second remark will be that we would like to have methods to extract concrete information, for example, large coupling behavior from this Fredholm determinants. So it's important to have, I mean, as a future direction, maybe it's important to have good tools to analyze these Fredholm determinants.
I'm not sure I am in good position to answer this question, because I didn't work actively on correlation functions, but on the quantum spectral curve side, I can only say something maybe not very pertinent, that you have this Grassmannian structure. So in any case, you have this smells like fermions, yes, determinants and asymmetric quantities, but I'm not sure it's a deep connection. I don't know any better analogy. Maybe it's relevant after all, but maybe some other people have. I propose, maybe, I don't know, maybe Benjamin has something to say on it.
He says no.
He says he doesn't.
More questions or comments? Yeah, Alison.
I have a little bit of a technical question concerning correlation functions and hexagon, because in AdS5, at least in the initial formulation of the hexagon, it was crucial to use the fact that the symmetries that commute with the Hamiltonian take the form of a tensor product of two copies of SU2/2. And also in AdS3, actually one manages to do the same thing using this trick, particularly in AdS3 cross S3 cross T4. Now, this is not the case in ABJM, which is at some point with some collaborators with, well, we tried a little bit to look at ABJM from that point of view, and it seems that it seemed hard to come up with a nice answer. So recently there was some interesting work in this direction, and to me, you know, it was a bit unpleasant not being able to come up with some nice answer for the ABJM case for correlation functions, because it seemed that this factorized structure doesn't seem like something very fundamental. I mean, integrability can be fundamental. Whether the algebra that you get factorizes in two copies, that seems a little bit of a little accident of life. So I was wondering if somebody maybe in the audience or maybe the people that have looked at this problem have some comment on this, you know, whether for this correlation function, this factorization is important or is just an accident that makes life a little bit easier, but is not so fundamental.
Yes, Charlotte. I think you're unmuted now. You can speak. No, actually, we cannot hear you.
You are muted, Charlotte.
Maybe can you write your question or comment? Can you try to speak? Okay, no, there is a problem.
No, it seems Charlotte is not muted. But we don't hear.
Okay, in the meantime, is there another question?
Maybe this. Is there somebody in the audience who can answer Alessandro's question? Or try to answer?
Ben, can you stand up?
No, I don't think I can really answer. I believe that this symmetry that you've mentioned is a real simplification, and we've seen it at work for n=4. I don't think it is fundamental, you know, to write down like the full set of bootstrap equations, but then it is a problem of solving them, and we know that it is in general a very difficult problem to. So if you don't have this simplification, then you will have to deal with a lot of matrix structures. There will probably be quite many of them. I think you've been looking at it actually in some situation. And so it looks like I mean, you would have to solve for all of these matrix structures and find relations. So additional relations that would possibly help you solve the problem. But that's very naively, because maybe somebody will find like a way around. Maybe we should not try to systematically apply the same strategy, you know, to any theory. And think about the specificity of each one. But I think also that there has been progress recently on ABJM and structure constant, but I don't know if like people like Shota or Yunfeng.
I was particularly curious about ABJM because of this recent progress. So I was wondering if maybe we could have gotten some comments on that. But apart from that, maybe I can also reformulate the question in a more like in a simpler way. do you or other people believe that anything for which we can solve the spectral problem should also be amenable to some sort of tessellation, hexagon tessellation formalism, up to the fact that it might be hard to find the right ansatz and the right factorization? So do you think that they go hand in hand, integrability for the spectrum and the possibility of doing this tessellation?
Well, so the tessellation itself, I believe will apply in general. If you have like a CFT and if you have a planar expansion, I believe you can formulate. I mean, this formalism, this strategy. But in practice, if you cannot solve, if you don't have integrability and if you don't have enough symmetry, you might not be able to do the first step, which is to solve for the form factors, if you are thinking about going along the line of the hexagons, for instance. So it's not going to be perhaps that useful in practice, because you will just, I mean, you will draw some nice cartoon, but you won't be able to translate them into concrete expressions or formulae. But the idea at the cartoon level, I don't see what could be wrong in trying to apply it to other theories. It just might not be very useful in some situation in practice. So.
Okay, there's a question by Pedro Vieira.
Okay. Yeah, no, just two small comments related to Alessandro's question. One is that I think this and just to complement what Ben just said, that this complication in AVJM with respect to the other two theories is not, I don't think it's unrelated to the usual complication that one has in CFTs with respect to odd versus even dimensions. It's usually the case that even dimensions are a little bit easier and things factorize more into SU2 times SU2 and so on. And for example, even in this fishnet limit, where sometimes people can construct the hexagons more explicitly, really from first principles, as Enrico would say, I see that he is not online. He tells me that doing it in odd dimensions versus even dimensions, it's really conceptually quite different and harder in odd dimensions. So I think we might also be seeing part of that in the lack of hexagons in AVJM. The second comment is that perhaps it's possible that other quantities related to hexagons might be easier to construct to get some data and some intuition. So as you said, there was this work by Shota. I also see that Shota is not in the audience, I think so. But I mean, in their paper, what they pointed out is that understanding better the structure of BPS operators and excitations on top of BPS operators is useful, because then they can produce data for this quantity we call math-Calais, this 3-point function between 1 non-BPS and 2 BPS. And they are systematizing better what is the space of such math-Calais in AVJM, because there's more than one there and things are a little bit richer. And so by staring at those math-Calais, I think this will be very, very useful data. Another piece of data that could be useful in AVJM, which is not directly the hexagon, but build of the hexagons, and this is something I'm trying to do with Enrico, is to study the octagon in AVJM, which is already the connection of two hexagons. And it could be that one is easier to find than the hexagon.
Okay, I will read Charlotte's question. She says to Volodya, I guess, you mentioned as an open problem the Coulomb branch. And you mentioned some rumors about its integrability. Could you elaborate on this?
No, it's, I know that people have been thinking for quite a long time on it, but I'm not aware of the results. Maybe somebody else can say about it, say, Kostya Shota is not in the audience, but maybe Kostya can comment on it. About the very possibility that this is integrable. Is Kostya in the audience?
I don't see him. Ah, no, yes, he's there. Can we unmute Zarembo?
I think I was unmuted. Okay. I have 2 questions. Yes.
And
sorry, could we first unmute Konstantin Zarembo?
Well, I just want to say that Coulomb branch is known to be integrable because on the string side, the boundary conditions do not violate integrability. And also there was a very beautiful work by Karanu and Hen about 7 years ago, who wrote down the spectral equations for this theory from integrability. But I'm sure there's more that can be done.
Especially in the view of your works, you, Charlotte, and a few co-authors about the brains, yes, about the integrability with brain boundary conditions for open spin chains. It should be, I mean, a way to understanding also the Coulomb phase this direction. Yes. How close it's how close are these two problems?
Well, I think that yeah, there is certainly a lot of interesting questions one can ask because this goes beyond the realm of CFT. This theory has a mass, so I think it relates to n=4 in the same way as QED relates to Maxwell's theory. So that there are massive particles that interact via exchange of n=4 CFT, and understanding their dynamics, I mean, would be extremely be much more rich in physics questions that one can ask. For instance, one can ask about the S matrix, which in n=4 well also exists, but it's equal to 1, strictly speaking, in 4 dimensions. So there are different type of quantum field theory questions one can ask. If integrability can be used to answer this, I mean, I don't know, but certainly some quantities that can be computed precisely by these methods that Volodya, you mentioned that Charlotte was working on, and which led to spectacular progress in boundary CFT.
Mm-hmm. Okay, there was a question by Anton. Are you commenting about this, Pedro? Okay, first Pedro. Sorry.
Yes. If I can, just let me just add one very quick advertisement that there was a nice paper by Frank and Simon Caron-Watt as well, a recent one where by exploring this 10D emergent symmetry in n=4, they also provide some more data about this Coulomb branch phase. And in particular, they have this proposal that the octagon can be interpreted as an amplitude in this Coulomb branch. So it will be another important piece of data. And so this gamma octagon would have an interpretation, putative interpretation, as the analog of gamma cusp in this phase.
Mm-hmm. Okay, now Anton.
Yeah, I think I had a question exactly along the lines what Kostya just mentioned on Pedro regarding this, but my question would be, I think, to Florian, probably, who is in the audience, and maybe to Volodya, regarding this massive Yangian dual conformal symmetry and the bootstrap program for the massive series. What I mean is that, as you, Volodya, mentioned, there is this double scanning limit of the gamma deformed n=4 plane one, which is goes to this conformal fishnet, and there is this conversation by Florian Lobert and other who developed this program for the massive case, and since they claim there exists analogous double scanning limit, but exactly from the n=4, but exactly on the Coulomb branch. So I was wondering exactly to confirm what Pedro is saying and Kostya, that I think it's very interesting maybe to devote this attention, because I have my motivation actually from the holographic side. Recently, we have in the AdS bulk, we have found solitonic type solutions of the D3 brain spikes, which must have a correspondence because John Schwartz in the past was having a work which was called gauge series in the Coulomb branch. And it is strongly believed, which he is describing, that such solutions are exactly must be duals of such gauge series which are defined on the Coulomb branch. So I think since in this solitonic type bubble solitons in the AdS5 bulk with the D3 spikes, they at the moment there are no holographic duals, and these are very interesting and promising candidates, because it looks like there is some emergent integrable structure behind, but at the moment holographically, because traditional holographic renormalization doesn't really work. So yeah, I was also thinking that that's extremely interesting point on the, to study the series. And the second one is probably a little bit more technical. I don't know if Florian can hear me. Florian, can you hear me? Or he could be unmuted, I don't know. Maybe Volodya, because they developed this booster program to compute this massive Yangian Fishnet type, Feynman integrals of the Fishnet type, which actually could be described by, this is d-dimensional, in principle d-dimensional realization, but it could be found by certain single valid representation, but I'm just, which is false for the result at one loop. I'm just wondering if they have thought what happens at high loop orders, if it could possess the same structure or not. And already maybe just directly to you, since this is to this, I was wondering if you have thought about this massive realization of the Fishnet from this n=4 Coulomb branch, or any other limits?
No, we have a paper with Shaposhnikov and Koronanas where we have presented some signs of the existence of this Coulomb phase, at least the flat vacuum, etc. Of course, they are a bit ugly, complex, etc. But they are certainly there. We didn't pose even questions about integrability of this branch which we found, so it's an open question. And of course, I followed a little bit the papers of Florian et al. I wanted to mention it during this discussion. The massive, it's indeed the massive branch, but the massive, say, if you speak about Fishnet graphs, they are all external. The massive propagators are external. They are the external legs. By the way, is it the case also for the planar limit in the full n=4? If you consider the Coulomb phase, it's maybe a naive question, but to the specialists.
You mean to possess the external incoming structure?
Yeah, but do you have also internal massive loops in this case? On the limits?
I think Pedro wants to. No, you say no.
No, it's again the.
It's easier if we could unmute ourselves more easily.
Yeah, maybe everybody can be
very
unmuted.
strict that you have to wait.
But certainly I didn't think deeply about integrability. Maybe it's better to ask Florian, of course.
Yeah, I'm addressing this concrete question. Florian, can you hear us? Or
yes, I can hear you. I had some problems to unmute myself, actually. Well, our approach was from the Feynman diagram side, right? We found these Yangian structures from the Feynman diagrams, and then we try to define a double scaling limit that gives a Fishnet theory which produces these Feynman diagrams as amplitudes. And well, at least at lower loop orders, they have this Yangian structure with external, where the external propagators can be massive. And yeah, we compared also the two situations, the one that Volodya mentioned, where you have spontaneous symmetry breaking, and the one that we introduced. The difference is that the masses in Volodya's case enter in as products in the propagators, and in our case they enter as differences, so more in this 5-dimensional spirit. And we only found these integrable structures for the difference masses and not for the product masses, so that distinguishes these two phases.
Yeah, right. But was this one loop result of the single series representation? Which is one loop result.
Well, yeah, we also find the symmetry at 2 loops, and at higher loops we have some numerical indications. Yeah.
Okay.
Actually, I don't know whether there are more people in the queue, but I'm impatient to ask a question to Andrea, if he is around. Cavaglia, Andrea Cavaglia. Is he here?
Yeah, he's here. You can ask.
It's about his, yeah, hi, Andrea. It's about his last talk, because I was quite fascinated by this bootstrap. Everything is called now bootstrap. I'm sorry, but this is the bootstrap of the end of his talk, when they try to bootstrap correlators using the spectrum, exact spectrum of the model. So, and you asked this question, whether the quantum spectral curve, the Q functions define completely the spectrum. Do you see already serious signs in this direction, I mean, from these numerics? And can you comment further on it? And also, do you see some possibility of analytic approach based on your bootstrap scheme?
So sorry, can you? So the first question is if we see signs that
yeah, essentially that the spectrum is completely enough, or maybe in other words, the Q functions, if you know them, are completely enough to define multi-point correlators, and or at least 4-point correlator. And also, do you see some analytic scheme which possibly can be produced out of your numerical scheme, so to put it on analytic basis?
Yeah, so let me start from the end. Well, one simple place to start for doing analytically would be to, for example, in the setup I presented, connecting with what Carlo and Pietro have been doing. And that would relate to the problem of first understanding how to solve the quantum spectral curve at strong coupling analytically, because there is an analytic bootstrap approach at strong coupling. But I'm sure there are many other regimes where one can try to do the bootstrap analytically, and people in the bootstrap community do it analytically in various limits. And for the first, so the signs that we see so far about how effective can this approach of combining integrability with the bootstrap can be are the ones I presented. So it's all yeah, but I think it's all to explore. Yeah.
So in your examples, it looks like you get very precise results, numerically very precise, if you just inject the spectrum and nothing else.
Yeah, and just 2 states in the spectrum. And yeah, the question is how, yeah, how to efficiently inject all the information that we have, that is in principle much more. And if we just ask abstractly, one would think that there is only one CFT with a spectrum of n equals 4. So it, in this vague sense, it contains all the information, but then how to use efficiently the bootstrap to compute things is another question.
No relation yet to I mean, other schemes like integrals over Q functions or this hexagon octagon expansion, no?
Not yet.
Not yet. Okay.
I ask a small question or make a small comment. I think, is it true that one of the very nice things about the setup that you considered is that you don't need to worry about double traces, which is not the case if you were to consider a 4-point function of usual 20 primes, say in n equals 4. Then you would have to consider really the non-planar spectrum as well, at least the double traces and the 3-point function with double traces and so on. So one of the things that's very nice about your defect is that you don't have these double traces, right? You can take the large n limit and it's purely single trace data that governs the 4-point function. Is this true? Am I remembering correctly or not?
Yeah, that is absolutely true. And well, the idea to explore how to study a local spectrum is to try to bootstrap all this, also this non-planar data that we don't have. And if there is a way to do this, maybe this mixing of planar and non-planar in the bootstrap can become also a resource to get information on non-planar physics. Maybe if we have all the planar solution from integrability, we can use it to.
Sure. Yeah, that makes sense. Thank you.
Okay, one last question. Yeah, in the back. No.
So we worked out this AdS3 example to the extent that we did for the hexagon, right? And I was at the same time enchanted and disappointed that the role of supersymmetry is the same. So this condition that the hexagon vertex is annihilated by the supersymmetry fixes the 2 excitation problem essentially, right? So then I thought, well, good. And then I thought, well, not good, because this must mean that you can't do anything that's not supersymmetric. But then again, if you turn it around and you say, well, the matrix part is there because there's supersymmetry, right? I mean, so the question is going to be, what are my chances to do tessellation and hexagon formalisms in integrable systems or CFTs which are not supersymmetric? Wouldn't that be a nice idea to try and get this to work for like the standard integrable models that have always been sitting there in cases like that?
Okay, so Pedro says fishnets.
No, that's it. That's just another example. Fishnets are nice because you can construct them, the mirror excitations from first principles, and there they are not supersymmetric, and they have a matrix part and so on. So Benjamin and João and Tiago and Enrico and so on have been working on them. I mean, they would say much better than me.
Okay, so if there are no more questions, we've had enough discussion. Let's thank Volodya.
Thank you. I only wanted to say that we can continue our discussion on Slack, which was very efficient, I think, for strings. Why not for IGST? And in principle, I liked this kind of discussion. This is a new invention of organizers of IGST. I greet it, but I hope it will be also a rotating obligation. But thank you for your active participation. You helped me. Thanks.